For over a century, plastic has transformed modern civilization. It is lightweight, durable, inexpensive, and found in almost every product we use. From food packaging and medical equipment to automobiles and aircraft, plastic has become one of the most important industrial materials ever created. Yet its greatest strength has also become its greatest weakness. Because plastic is designed to last, billions of tons now exist in landfills, rivers, and oceans. Traditional recycling systems are struggling to keep pace, forcing engineers to ask an important question. What if plastic waste is not rubbish at all, but a valuable energy resource waiting to be recovered? Most people think recycling means melting plastic down and turning it into another plastic product. While mechanical recycling plays an important role, it has significant limitations. Plastic degrades every time it is reheated. Different polymer types often cannot be mixed. Contamination reduces quality, and many plastics simply cannot be recycled economically using traditional methods. As a result, only a relatively small proportion of global plastic waste is mechanically recycled, while much of the rest is buried, burned, or escapes into the environment. A new generation of technology is attempting to solve this problem by treating plastic very differently. Instead of recycling the material itself, engineers are breaking it down into its original chemical building blocks. This approach is often known as chemical recycling or advanced recycling. One of its most promising techniques is pyrolysis, a process capable of converting certain plastics back into an oil-like substance that can be refined into new fuels or used as feedstock for manufacturing fresh plastics. The science behind pyrolysis is remarkably elegant. Plastics are made from long chains of hydrocarbons known as polymers. These polymers were originally created from petroleum or natural gas. Pyrolysis reverses much of that process. Plastic is heated to extremely high temperatures, typically between 400 and 700 degrees Celsius, in an oxygen-free environment. Without oxygen, the material does not burn. Instead, the long molecular chains break apart into smaller hydrocarbon molecules. The result is a mixture of gases, synthetic oil, waxes, and solid carbon residues. Depending on the feedstock and operating conditions, much of this output can be refined into valuable industrial products. In effect, plastic is transformed back into a petroleum-like rather than simply becoming waste. Automation is rapidly becoming central to these facilities. Modern chemical recycling plants increasingly rely on robotics and artificial intelligence to improve efficiency and consistency. Robotic sorting systems identify different plastic types using cameras, spectroscopy, and machine learning algorithms. Conveyor systems automatically separate unsuitable materials before they reach the reactors. This reduces contamination while improving the quality of the final products. Artificial intelligence also monitors the recycling process itself. Hundreds of sensors measure temperature, pressure, gas composition, flow rates, and chemical output continuously. AI systems analyze these variables in real time, adjusting operating conditions to maximize efficiency and product quality. Instead of operators manually controlling every stage, autonomous systems optimize production around the clock. The robotics extend beyond sorting and monitoring. Automated handling systems transport shredded plastic into reactors, remove processed materials, inspect equipment, and manage maintenance schedules. Predictive maintenance software identifies components likely to fail before breakdowns occur, reducing downtime and improving safety. Entire facilities are becoming increasingly autonomous. This transformation is important because global plastic production continues to rise. Hundreds of millions of tons of plastic are produced every year, supporting industries ranging from healthcare and food preservation to electronics and transportation. Completely eliminating plastic is neither practical nor necessarily desirable. The challenge is managing it responsibly after use. Traditional landfill disposal wastes valuable carbon resources. Plastic contains significant amounts of stored chemical energy because it originated from fossil hydrocarbons. Chemical recycling seeks to recover that value rather than burying it underground. In principle, plastic becomes part of a circular industrial economy where materials are repeatedly reused instead of discarded. Energy efficiency remains a major area of research. Pyrolysis requires substantial heat input, raising questions about its overall environmental performance. Engineers are therefore developing reactors that recover waste heat, improve thermal efficiency, and integrate renewable energy where possible. Some facilities even use gases generated during pyrolysis to fuel parts of the process itself, reducing external energy requirements. Different plastics behave differently during chemical recycling. Polyethylene and polypropylene, common in packaging and consumer products, generally perform well. Other materials require additional processing or are less suitable for pyrolysis. Researchers continue improving methods capable of handling increasingly diverse waste streams while minimizing unwanted byproducts. Environmental considerations remain central to the debate. Supporters argue that advanced recycling diverts plastic from landfills and oceans while reducing demand for newly extracted petroleum feedstocks. Critics caution that chemical recycling should not replace efforts to reduce unnecessary plastic production, improve product design, and expand traditional recycling where appropriate. Most experts view chemical recycling as one component of a broader waste management strategy rather than a complete solution. Economics will ultimately determine how widely these technologies spread. Chemical recycling facilities require substantial investment in reactors, robotics, automation systems, emissions controls, and refining equipment. Their success depends upon reliable supplies of waste plastic, efficient operation, and market demand for recycled feedstocks. As technology improves, operating costs continue to decline while product quality improves. Several countries are already investing heavily in these systems. Europe, North America, and parts of Asia are constructing advanced recycling facilities designed to process plastics previously considered unrecyclable. Governments increasingly recognize that waste management, energy security, and industrial sustainability are closely connected. Plastic is no longer viewed simply as refuse, but as a strategic industrial resource. Major chemical companies are participating as well. Many manufacturers aim to increase the proportion of recycled content within future products. Chemically recycled feedstocks can often produce plastics with properties comparable to virgin materials, making them attractive for demanding applications where quality is essential. The implications extend beyond packaging. Future recycling systems may process plastics recovered from vehicles, construction materials, consumer electronics, textiles, and industrial equipment. Autonomous facilities operating continuously could become essential components of modern urban infrastructure, quietly converting waste into valuable industrial feedstocks. Artificial intelligence may accelerate this transition further. Machine learning systems continue improving their ability to identify polymer types, predict reactor performance, optimize chemical yields, and reduce energy consumption. Digital twins, virtual models of entire recycling plants, allow engineers to test operational changes before implementing them in real facilities. These technologies improve both efficiency and reliability. Some researchers envision highly distributed recycling networks. Instead of transporting enormous quantities of waste over long distances, smaller autonomous facilities could operate closer to the source of plastic generation. This would reduce transportation costs while creating more resilient local recycling systems. Despite the progress, challenges remain. Chemical recycling cannot process every type of plastic equally. Contamination, mixed materials, and economic factors continue influencing performance. Collection systems must also improve to provide consistent supplies of suitable waste. Public participation in waste separation remains important even as automation becomes more sophisticated. Nevertheless, the direction is becoming increasingly clear. Waste is gradually being redefined as feedstock. Materials once destined for landfill are now entering advanced industrial processes capable of recovering both chemical value and energy. Robotics, artificial intelligence, and molecular engineering are transforming recycling from a largely mechanical activity into a highly automated chemical industry. The broader lesson is that industrial systems are evolving toward circularity. Rather than following the traditional model of extract, manufacture, use, and discard, future industries increasingly seek to recover materials at the end of their useful lives and return them to production. Plastic, once regarded primarily as an environmental burden, may become one of the most valuable secondary resources in the global economy. The age of simply throwing plastic away is slowly coming to an end. In its place, a new generation of robotic infrastructure is emerging, capable of dismantling complex polymers molecule by molecule and transforming yesterday's waste into tomorrow's raw materials. The landfill of the future may no longer be a destination for discarded plastic. It may instead become the world's next great resource reserve. If you enjoyed this deep dive into the forces shaping our future, be sure to explore our other documentaries examining the technologies redefining modern civilization. And if you want to keep exploring the biggest questions about science, power, and the future of humanity, make sure to subscribe to the channel and join us for the next journey into the unknown.